Okay, in this section, we're looking at a new kind of integral. Section 15.2 is on line integrals, and this video is going to cover scalar line integrals. We're also going to look at line integrals over vector fields, but we will do that part in class. So we started with integrals of single variables back in Calculus 1. We integrated over intervals in the real line. We also did double and triple integrals where we integrated over regions in R2 and R3. Line integrals, which again are kind of mislabeled as is pointing out here. They really should be called curve integrals, but that's okay. It's another class of integrals that are part of this chapter. And what you do with them is you integrate scalar valued functions or vector fields along different curves. Okay, so let's first start by looking at this interactive figure. So we're going to do scalar line integrals in the plane. So first consider line integrals of scalar valued functions over curves in the plane. We have a surface and a parameterized curve C in the xy plane. We're going to, just for the purpose of this figure, assume that f of xy is greater than or equal to 0 for everything on the curve, so that we can think about this in terms of like an area. Now, consider a curtain-like surface formed by the vertical line segments joining z equals f of xy and c. The goal is to find the area of one side of this curtain in terms of a line integral. As with other integrals we've studied, we can do this with Riemann sums. Okay, so basically what this line integral, which really should be curve integral, is getting us is the area of a curtain that goes from the curve in the plane up to the surface. And as you move A and B around, you can change which little piece of the curtain you're looking for as you set these bounds A and B, but that's basically what it does for you. Okay, they go through some derivation of, again, breaking this up into little rectangles and doing the same sort of little game that we've done many times before, where you make infinitely many little rectangles, and however you pick your little k's, and then let the size of the rectangle go to 0, and things that we're used to doing. Okay, the first definition that they give, which is the one you derive from the Riemann sums, is a scalar line integral in the plane using an arc length parameter. Here you have the definition given with a limit of Riemann sums. Okay, again, we're not actually going to do it that way. We often start with arc length because that's what comes out about when you do the proofs. But what we really want to look at are parameters other than arc length. And basically what we'll do to do that is do an r prime of t dt to convert from ds to dt. So we can use any parameterization that we want. So actually, if we want to evaluate scalar line integrals in R2, and we have some curve that's given by any parameterization x of t, y sub t, we've got bounds on t from a to b. We're just integrating from a to b our function with our parameterization, r prime of d dt. And then remember, r prime of t is square root of x prime of t squared plus y prime of t squared dt. Okay, so that's what we're going to do. So we have a procedure then. If we want to do this, we have to get a parametric description of our curve. Sometimes it's given to us, sometimes it's not. We have to compute this magnitude of r prime of t. That's like a speed factor that we have to get. That's x prime of t squared plus y prime of t squared, take the square root. We make the substitutions and we evaluate this plain old integral that we already know. Okay, let's take a look at finding the temperature of the circular plate. R equals x of y with x squared plus y squared less than or equal to 1. We have a function that says its t of xy is 100 x squared plus 2y squared. And we want to go We want to confirm the average temperature, and we have the parametric description of the circle as x is cosine t squared, y is sine t squared, and t goes from 0 to square root 2 pi. Okay. So you can find the speed factor, magnitude of r prime of t. That turns out to be 2t. Making substitutions into our line integral. We're going to be integrating our function, which was this cosine t squared sine t squared. So we're going to be integrating, oh, sorry, that was our curve. So we're integrating t from 0 to square root 2 pi. We have our function, 100 x squared plus 2y squared, which becomes a cosine squared t squared plus 2 sine squared t squared. And then we've got our speed part, 2t dt. That integral turns out to be 300 pi. If we wanted to then find out the average temperature on the boundary of the plate, you could divide by the length around the boundary, which this was a circle of radius 1. So that's 2 pi. So we do 300 pi divided by 2 pi and find out that the average temperature on the boundary is 150. Okay, not too bad. Line integrals in R3 turn out to be basically the exact same thing, whatever parameterization you want. And then we got the speed factor, which now you just add a z term onto. Here's a couple examples of line integrals. Say we want to integrate in R3 this integral xy plus 2z ds on the following line segments. The first one, 1, 0, 0 to 0, 1, 1, and then the second one in reverse. So you have to start, again, we're following the procedure we had up here. You have to find a parametric description of your curve. So we need a parametric description of going from 1, 0, 0 to 0, 1, 1. Well, if you remember parameterizing lines way back in chapter 12 when we started, we can start with 1.100, and then we have to come up with a factor here that's going to kind of make it work out for us. Well, what happens? We go down 1, up 1, up 1. So down 1, up 1, up 1 times t, and we're going to let t go from 0 to 1. That's an easy parameterization. There are other parameterizations you could do, but that's one that works out. So that's what we have. You then go in and calculate the speed factor. Turns out to be the square root of 3. Our parameterization here, we have x as 1 minus t, y as t, and z as t. So if you plug into the function we're trying to integrate and get the new form of that, then actually do the integral, you get 7 root 3 over 6. Now going with this part B here, we're going from 0, 1, 1 to 1, 0, 0. I'm basically doing the same thing, but we have a different parameterization. We're going to start at 0, 1, 1. And then to get to 1, 1, 0, we're going to go up 1, down 1, down 1. So you can see our form for that one. Up 1, down 1, down 1. And again, t is going to go 0 to 1. Again, the speed is square root of 3. And substituting in and doing the same kind of things that we did before, it turns out you again get 7 square roots of 3 over 6. So this tells us it doesn't matter how we parameterize this curve. It's going to work out to be the same. Also doesn't matter which way you orient your integral, whether you go from this point to that point or that point to this point, it's going to work out the same. So kind of a neat thing. Okay. I just want you to try a couple of these. All right, let's try number 15. So for these, you're doing a scalar line integrals in the plane. Find a parametric description for C in the form. If it's not given, evaluate R prime of t and convert the line integral to an ordinary integral with the respect to the parameter and evaluate it. So just try number 15. and number 17. That should work out pretty well. Actually, never mind. Let's do number 17 and number 18. I like that one a little better. So no number 15. Let's do number 17 and number 18. Okay, thanks.